So, college algebra, section 4.5, solving exponential and logarithmic functions. This will probably take 3 videos just because it's kind of a long section. It's not really hard, it's just a little bit long. And one of the things that we're going to be doing in this section 4.5 and then again in 4.6 is the stuff on logarithmic logarithms that you did in 4.3 and 4.4 are going to project over into 4.5 and 4.6. It's where you're going to start using that information. So we're going to do equations, and you'll find out that what you did, especially in 4.4, is going to be very helpful in solving these equations. So one of the key things that I need to show you, and we talked about it, I referred to it a little bit in one of the other lessons, is when you have something in exponential form right now and your exponent is a variable, in order for you to solve for the variable, the x, the base numbers must be the same. You can't solve it without that happening. So I'm going to write 2 to the 5x equals 2 to the 6th power, because 2 to the 6th power is 64. Alright, if that's the case, then we can say that because the bases are the same, the exponents are the same, so we get x equals 6 over 5. Okay, so that's true. You've got to make 2 as your base instead of 64. Alright, but one of the things with this particular problem is it's very easy to just take 64 and make it 2 to the 6th. But what if you had a number like 27? Well, 2 to what power gives me 27? There isn't a whole number. You can't use like 2 or 3 or 4. It's going to be a decimal. And that's where the logarithms come in, is so you can make this base actually a 2 to some power, okay, or a 10 to some power. So that's what we're going to be doing in this section, is being able to solve equations where it's not so easy and cut and dry to actually solve these. So the base exponent property is pretty much what I just said, that if we have a base with a variable or a number, and we have another one, and I'm saying that they're equal, because the bases are equal, the exponents have to be equal. Okay? And that's when this number is not 1. Okay? A has to be a number bigger than 0. That base number has to be bigger than 0. Alright, which brings us to example 2. And example 2 is 2 to the 3x minus 7 equals 32. Alright, so again, we're going to make that into a 2. 2 to the 2, 4, 8, 16, 32. 2 to the 5th power. So because the bases are the same, 3x minus 7 equals 5. And you just solve for x then, and when you solve for x, you get 4. Plug it back in, see if it's true. It is. Life is good. Alright, another property that's going to be helpful is the property of logarithmic equality, bottom of page 399. So when we have a log that has a base, and then we have an m, and then we have another log, a n, okay, that means if these two are equal, notice the bases are the same, if these two are equal, if the bases are equal, then this number and this number have to be equal. Okay, so if we can get the bases to be the same, then this and this are going to be equal. Alright, so, and again, a has to be greater than 0 and cannot equal 1. So a key thing that happens here is if you have 2 logarithms and you cannot make, if you have an equation written in exponential form, like 3 to the x equals 20. Now I said this earlier, that sometimes you just can't make that and that base the same. I can't make that 20 into a 3, and I said that's where logarithms come in, and that's what we're going to do here. When you have an exponential equation like that, and you can't take the 20 and make it 3 to some power, all you have to do is take the log of each side. Okay? So, then we put our x in front. So far I'm just doing algebra, nothing really weird. Okay, and then I'm going to divide by log of 3 because I want to isolate the x, so I'm going to divide both sides. So x then equals this right here. So you get your handy dandy calculator out, put the log of 20 in there and the log of 3, and then divide. And you will get 2.7268. Now that 2.7268 is an estimate, okay, when you take the log of that. This is the exact answer. If you do not have a calculator, this is the exact answer. It's kind of like saying the number 2/3 is a fraction. That is an exact answer, but when you put it in your calculator, you get 0.66666 into infinity. This is not the exact answer because the answer goes on and on and on. The 2/3 is the exact answer. So it's the same with logarithms. The fraction here is actually the exact answer. When you put it into your calculator, this goes on forever. So this is just an estimate, and that's why I use the sorta symbol. It's sorta 2.7268. Okay, so let's keep going. Okay, so we had that 3x of 20. And then what we did is we took the log of each side. Well, what is the base on this log? Well, the base is 10, right? So it doesn't really matter what base we use. It's just easier because our calculator uses the number 10. If we were to use a different log, like let's say that we decided to use a base 3 log instead, okay, and if you look back at page 394, when we have these two are the same, this whole thing then equals x, right? And since our calculator won't do base 3, we have to change that. So we do log of 20 over log of 3. And if you look back at your notes, that's exactly what we came up with when we did example 2 using the log with a base 10. Okay, so this maybe took a little longer, but I just wanted to show you that you don't have to use log of 10. You could use log of any base you want, and the base you're going to want to choose is the one that is the same as this number here, so that they both cancel out. Your logs cancel out and you're just left with x. But anyway, that's just a freebie there at the bottom of page 400 talked about a little bit. Alright, so let's take 4. And you have something like that. Alright, so what do we do with that? Same thing. If we have an exponential form and we have different bases, we take the log of each one. Oops. Gosh. Alright, let's make that into a 3. Okay? And you're thinking, okay, why does that help so much? Because that takes my exponent here and moves it in front. Put it in parentheses because it's the whole exponent, just not the 3. Oops. Let's make that a negative x log of 3. Alright, so what do I do with that? I distribute these two right here. So then I get x log 4 plus 3 log 4 equals negative x log 3. You see how I distributed this? I took this log of 4 and multiplied it by x, then I took the log of 4 and multiplied it by 3, and got this and this. Alright, so let's keep going here. I'm going to move some things around. This has an x in it and this has an x, so I'm going to move this whole thing over here and this thing here over here. And so I get x log 4 plus x log 3. And add that to both sides because this is negative, and this is going to be a negative over here. Okay? Alright, so why did I do that? Because I have an x there and an x there, and I can factor that x out. And the reason I want to factor that x out is because then I can divide both sides by everything else and get the x isolated. And that's the key thing, is I'm trying to find x, so I have to isolate it. So I get that. So then I divide both sides by log 4 plus log 3. So this all goes away. And I can solve this with my calculator. Log of 4, take that answer, multiply it by negative 3, divided by the log of 4 plus the log of 3, and I get a number, again, similar to, sort of like, negative 1.6737. Alright, so what does that number mean? That means that 4 to the negative 1.6737 plus 3, that's going to give me a number up here of 2.3 something. So 4 to the 2.3 something is going to be the same as 3 to the negative, which would be 3 to the positive 1.6737. So if you did put that into your calculator, if we took 4, well, let me erase a bunch of stuff here. I do want you to understand what in the world you just found, because so many times, you find these answers, it doesn't really help you a whole lot, does it? Okay, put it all back. Alright, so we got for an answer x equals negative 1.6, let's just 737. Okay, so that means 4 from up here to the negative 1.6737 plus 3 equals 3 to the negative 1.6737. So if you take your handy dandy calculator and add those two together, you're going to get, like I said, 2.33-ish. So 4 to the 2.33-ish, I mean, we get different than that because of the decimal goes further, equals 3 to the 1.6737-ish. So if you take your calculator and plug 4 to the 2.33 into it, I guess no, it'd be 1 point, wouldn't it? I'm sorry. Because this here, when I take negative 1.6737 and add 3, I'm going to get 1.33-ish here. And so I put 4 to the 1.33 in my calculator, and I put 3 to the 1.67 in my calculator. I'm going to get a number very, very similar. They're going to be pretty close to being equal. And the reason they're not going to be equal is because of me rounding the decimals. Okay, so that's it for the first video.